Hubble, a technological marvel unraveling the secrets of the universe. A telescope so extraordinary, it's expanding our understanding about the fate of galaxies and introducing us to massive forces we never knew existed.
It's an iconic symbol of success, of American ingenuity.
Hubble has revealed black holes and supernovae, astrophysical jets, and bubbles floating in space. And it's taken on pop culture status.
People all over the world have been inspired by the beautiful images that Hubble has taken.
Now, Hubble is paving the way for the birth of a new telescope, 100 times more powerful. Thanks to Hubble, we're entering a new era of exploration and going deeper into space than ever before. The most celebrated telescope on Earth never touches the planet. Launched in 1990, the Hubble Space Telescope has been in constant orbit 350 miles above us for more than 25 years. It completes one revolution around Earth about every 96 minutes. Hubble's powerful gaze sees it all, thanks to a collaboration between teams of scientists and engineers from NASA and the Space Telescope Science Institute in Baltimore, Maryland. Ken Senbach, one of the early Hubble Project scientists, is now the director of the institute.
With Hubble, you can peer back almost to the beginning of time as we know it. You can peer back 13.4, 13.3 billion years. Hubble's up above the atmosphere, so it can see light that you can't see on the surface of the Earth, even on high mountains.
Where other ground-based telescopes and smaller telescopes run out of power and resolution, Hubble is just getting started.
It weighs about 24,000 pounds.
Building the 12-ton eye in the sky was an unprecedented scientific feat.
The Hubble Space Telescope has a mirror that's 8 feet across, okay? So that's the size of the diameter of its mirror. So this is much bigger than any telescope that you've ever used from your backyard. But what's most impressive about it is that we put it into space. So in order to do that, it has to use very small amounts of power. It only uses the same amount of power as a hairdryer. It travels around the Earth in its orbit at something like 10,000 miles per hour. And it orbits the Earth every hour and a half. So it's whipping up there. So if you can catch it, it's not like it's at some fixed point. It's going to come streaking across the sky pretty quickly.
Hubble sends back picture data in black and white. Then, image experts like Zsolt Levay at the Space Telescope Science Institute assign colors to these images according to the chemical elements detected by Hubble's instruments. Blue shows oxygen. Red shows sulfur, and green is hydrogen. Motion is added based on additional data.
The mission of Hubble doesn't stop with the pretty pictures. This data all comes down to an archive. In that archive is every bit of data that has ever been taken by the Hubble Space Telescope, and it's continually updated every few hours as new data comes down.
Anybody in the world can write a proposal to use Hubble, and as a result, there are more than 800 scientific papers published every year based on Hubble observations.
Not long after its launch, scientists turned to Hubble to provide visible evidence that the violent forces that create stars far off in space also shape our own solar system. In the summer of 1992, comet Shoemaker-Levy 9, or SL9, passed too close to Jupiter. The mile-long comet is trapped by the planet's gravity. SL9 breaks apart. The fragments spread into a long single line, seen in a Hubble image called the String of Pearls. Data suggested these pearls would soon collide with Jupiter. So planetary astronomer Heidi Hammel submitted a proposal to NASA.
We have known for many, many decades that collisions are an incredibly important part of solar system evolution. You look at the moon and you see craters. So you know that collisions are important. Even on the Earth, we've known for decades that collisions have played a big role, but we never have had an opportunity to see a collision.
In July 1994, the team gathered at the Space Telescope Science Institute in Baltimore to watch the comet make contact with the planet.
We didn't know what was going to happen when Shoemaker-Levy 9 hit Jupiter, and it was really possible that nothing would happen at all.
The first image of Shoemaker-Levy 9 came in. It showed no signs of impact. But then, new images came in.
So there's a red spot, so you know. Atlas
Oh,
yeah, that's it.
my God.
That's it.
Look at that. The planet had rotated enough that the impact site was visible on the disk, and it was huge.
The team watched the comet hit the planet in real time. It's cosmic history in action. The press stood by in an auditorium above.
And at the same time, on the screen of the press conference, Gene Shoemaker was saying,
if we should see these things at all,
and we were downstairs going, whoa, look at this, amazing. And we go, oh, we have to show this. You can't let him sit up there saying we don't know. We know.
and I think we may have some up-to-date information from Heidi Hamel.
I have a raw laser printer output. This is as raw as it gets. We can actually see the impact site itself.
For an entire week, Hubble captured images of Shoemaker-Levy 9 as it mercilessly hammered Jupiter.
We calculated the heights of these explosive plumes out of Jupiter to rising something like 3,000 kilometers out of Jupiter's atmospheres. It's huge. It's planetary-wide scale. What there was left was clouds that had been seriously disturbed over thousands and thousands of miles, seriously disturbed up to temperatures of tens of thousands of degrees.
Hubble's pictures of the comet impact proved that the violence that formed our planet billions of years ago continues through this day.
Hubble provided this unprecedented kind of upgrade on any pictures that had been taken from the ground before.
The cameras and other equipment aboard Hubble aren't immortal. Over the years, they've needed tune-ups and upgrades in order to keep sending us astounding pictures of the cosmos. But servicing a speeding telescope orbiting 350 miles up in space has its challenges.
The kinds of things that we've done go into the components, the organs, the instruments that are in there, and either take out whole instruments and replace them with new ones, or even open up those instruments. It's kind of like doing surgery in space.
Liftoff of Spaceship Flight.
Shuttle surgeons made a house call in May 2009. It will be the last Hubble rescue mission. A new, higher resolution telescope is in development. But at 19 years old, Hubble was nowhere near retiring. In 2009, it just needed some TLC. One of the astronauts ready to take on the upgrade mission was John Grunsfeld.
Going to Hubble is a calculated risk. Spaceflight is risky by any means. So in the scheme of things, this is something that I've determined, and on behalf of my family, that it's worth risking my life for.
When the shuttle astronauts finished, Hubble was saved, and more powerful than ever. It had received its third wide-field camera, this one with greater resolution.
Hubble's new camera can see infrared light, so it can see further back in time and find galaxies that formed earlier in the universe than the original deep field showed.
Only a handful of astronomical objects have been observed by all three of Hubble's wide-field cameras. One object is the Hubble Nebula, a massive, seething star blowing an expanding bubble light years across.
When a star that's 45 times as large as the sun is blasting out energy, it really makes a big impact. If you blow a bubble out of a, it's a normal bubble, right? What keeps it looking like a bubble is the fact that it's running into that air resistance, right? The air is keeping it constrained. The pressure is keeping it shaped like that bubble until you pop it. The Hubble Nebula is like that situation. This star is blasting out enormous amounts of energy, and that energy is slamming into not air, but the gas and dust cocooning this region. It's carving out, it's essentially a little explosion, carving out a bubble in space. And you can see that it's run into a little bit more resistance on this side than this side. In this visualization, we've taken a true image taken by the Hubble and other space telescopes and turned it into a fly-through. Up here is gas and dust that is occulting and blocking part of this expansion. And in these gas clouds, many, many new stars are being born and influenced by this bubble that's expanding.
One of the largest and most ambitious Hubble programs was the Panchromatic Hubble Andromeda Treasury, or FAT.
Hubble was able to see the Andromeda galaxy as a collection of millions of individual stars. That's what a galaxy is. It's a collection of individual stars. And with the resolution of Hubble, we're able to see individual stars in this other galaxy that are separated by the same distance as the distance between the sun and the nearest star to the sun.
The FAT project measured the brightness and colors of nearly 120 million individual stars.
We're able to answer fundamental questions about how stars form and evolve to make galaxies through this remarkable Hubble image.
While new clues unfold about the possibility of life on other planets, Hubble's been helping scientists piece together the life cycle of stars. In spring 1995, Jeff Hester of Arizona State University knew that stars evolve from clouds of gas and dust. But what he doesn't know is how these clouds give life to stars. In 1995, astronomers suspected that the Eagle Nebula in the constellation of Serpens might provide clues to how clouds give life to stars. Even the most powerful Earth-bound telescopes can't get a clear view. Jeff Hester of Arizona State University aimed Hubble Space Telescope toward the Eagle Nebula. As he downloaded his images from Hubble, Hester... For the first time, scientists saw that each pillar was dotted with small clumps of gas. Could such clumps be a missing link in the birth of stars? Hester called the clumps evaporating gaseous globules, eggs for short. The image reveals that forming inside some of the eggs are embryonic stars.
What we're looking at is a snapshot of a very dynamic process, a snapshot of something that's changing. As part of that change, next generation of stars is emerging. This one, for example, you can see the little red dot in there, which actually is the star. And that one is an especially nice one. The star at the tip of the egg is actually pronounced.
In the photograph, the eggs appear small, but our entire solar system could fit comfortably inside each one. These hot clumps of gas are the first stage of the formation of a star. And the towers where they hang are rightfully called the pillars of creation. Hubble's image of the Eagle Nebula shows us an early stage in the creation of stars. What it doesn't show is the next stage, how stars hatch from eggs. That answer came from images Hubble captured in 1994 in a nebula some 1,500 light-years away in the Sword of Orion. Like the Eagle Nebula, Orion is a birthplace of stars. When scientists closely examined this image, they discovered tiny dark spots, flattened disks of gas and dust spots created by recently hatched eggs. The spots are called protoplanetary disks. As the baby star grows in the center, the protoplanetary disk heats up and turns into a planet-making factory. Countless tiny particles of dust hanging suspended in the gas. Dust that is 1,000 times smaller than grains of sand stick together in cosmic dust bunnies. Over hundreds of thousands of years, these dust bunnies gradually build up into small asteroids, moons, and planets. Eventually, the gas is gone, fallen onto the newborn star, or blown away by stellar winds, leaving behind a newborn planetary system.
It really is the case that if you could go back 4.5 billion years ago and look at the formation of the sun and the solar system, that it would be that kind of an environment that you would find us in.
We can't go back 4.5 billion years, but fast forward 2 decades from Hester's initial groundbreaking research, and Hubble is providing us with new information.
So in 2014, we revisited the pillars of creation, here seen in visible light, and then here stepping just a little bit into the infrared with Hubble's Wide Field Camera 3. In this picture, we see right through the cloud into the stars that are being born inside those pillars and beyond the thousands of stars in the background behind it.
Hubble telescope observed something else about clouds and the birth of stars. Astrophysical jets. Use a little imagination, and they look like Star Wars sabers. But what they are is the result of a star at the beginning of birth when it's first formed, trying not to blow up.
It's spinning so fast that it's shedding material, it's losing stuff, but only in these tight columns of incredibly fast-moving gas.
It's like water from a hose, but it's sprouting from a star.
You're basically seeing the history of the ejections from the star over the past, say, 1,000 years.
The jet is a snapshot of time, of a birth process that could lead to more solar systems like ours. But where there's birth, there's death. In 2004, Hubble captured an image that gave us a glimpse of our eventual demise. The Helix Nebula. As these outer layers of a star expand, they leave behind a searing hot ball of solidified oxygen and carbon astronomers call a white dwarf. Someday, the same thing will happen to our own sun. The sun will run out of fuel, and that will cause it to expand into a giant red star. That's bad news. The temperatures on our planet will rise over 1,000 degrees. All life on Earth will perish. A wall of hot gas will sweep over the Earth, through our solar system, and into space. Every planet and moon in its path will be incinerated. The only thing left of our sun will be a splash of color visible from thousands of light years away. Like this.
So the human race has its warning. We have 5 billion years to clear out of town.
But the death of our own sun pales in comparison to a much more powerful downfall we've caught a glimpse of, thanks to Hubble. Some stars are over 100 times more massive than our sun. The bigger the star, the shorter its life, and the more violent its death. These stars explode in a massive fireball called a supernova.
Not every kind of star can explode as a supernova. The sun can't, for example. It just lacks the oomph. It doesn't have the mass that you need to be able to get what happens in the core to make a star blow up. There are a handful of stars in the galaxy that are definitely capable of doing this.
Every star is carefully balanced between the inward pull of its gravity and the outward pressure of the heat it generates from nuclear fusion. When it runs out of fuel, the pressure needed for balance is gone. Gravity now reigns supreme. The star caves in and explodes. The full fury of a supernova destroys the star and everything around it. One such giant star has already exploded in our own galaxy, the Crab Nebula. Hubble Telescope recorded the aftermath.
The Crab Nebula is the expanding wreckage from a supernova that occurred in the year 1054. The explosion of the supernova was recorded by Chinese astronomers, so we know exactly when the explosion was.
The expanding debris from this 1,000-year-old supernova is still moving into space at over 3 million miles per hour. But Hubble's image is more than just a snapshot of ancient history. For scientists, the interconnected web-like filaments offer a clue to the nature of life itself. The basic elements needed to create life are formed in the heart of a star. When stars explode, these fundamental elements are scattered throughout the universe, seeding distant nebula clouds that give birth to new planets and new life.
The hemoglobin in your blood, when you bleed and it's red, that red color is due to oxygen, and it's due to iron that is in your blood that was created in a supernova. The gold on your wedding ring is created in a supernova. Calcium in your bones was created in a supernova. And so we learn so much about the universe itself when these stars die.
But some mysteries remain.
One of the biggest mysteries related to the Crab Nebula today is where all of the material is. We know that the star that blew up to form the Crab Nebula had about 10 times the mass of the Sun. We can only measure about half of the mass of the star that blew up the Crab Nebula.
Scientists believe the star lost mass before it exploded into a supernova. Gas we can no longer detect. Hubble is giving scientists the ultimate learning experience by monitoring one particular star, Eta Carina, back in the Carina Nebula.
This is a star that is a bit of a mystery. It appears to have about 100 times the mass of the Sun, and that is the upper limit. The more massive a star is, the hotter it is, and the surface of the star is so hot that it can't even hold on to its own gas. It's constantly blowing off a stream of gas.
For over a decade, Hubble created a series of photos of Eta Carina. The photos show two enormous lobes of superheated gas erupting from the surface. Although Eta Carina is a young star, its huge mass makes it unstable. This star will not survive for long.
This is one of the very few stars that we can point at and say, yeah, that one's gonna go.
When the star Eta Carina explodes, it will become one of the most devastating supernovae ever recorded.
When the light from the explosion reaches us, it will be an extraordinary sight. It will be almost as bright as the full moon. All that light concentrated into a point of light in our sky. It will cast shadows at night.
The fireworks will begin when the star runs out of fuel. The gigantic star will destroy itself in just a few seconds. The core of the exploding star will bear the full brunt of the catastrophe. When that happens, it will leave behind the one outer space phenomenon that has long captured the imagination of stargazers: a black hole. Before Hubble, there was no conclusive proof that black holes existed. The modern concept of a black hole comes from Einstein's theory of general relativity.
If you take matter and you make it massive enough, dense enough, the gravity will be so strong that you'll create a region of space that light can't get out of. It truly does make a hole in space. You can get into it, you can't get out of it. It's sort of like a cosmic lobster trap.
According to Einstein, a black hole begins with a very large star. It must be at least 4 times bigger than our sun.
A black hole is a simple thing. It is a hunk of matter which somehow has gotten so small that the gravitational field right around it is so strong that light cannot escape from it.
And since nothing can travel faster than the speed of light, we receive no information from that object, and so we call it a black hole.
During the blast of a supernova, the inner core of a star collapses into a single point, smaller than a pinhead. Astronomers call this single point a singularity. A singularity is an object with no length, width, or height, yet it retains most of the gravity of the original star. One of the primary goals for Hubble was to prove once and for all whether or not black holes exist. But how do astronomers search for an invisible point? They decided to focus Hubble on the centers of galaxies. What they found were stars zooming around at very high speeds. This is not how stars normally behave. Most stars move along at relatively slow speeds. But down in the central hub of galaxies, stars are being thrown around by the gravity of something massive, yet ultra-compact. There can be only one cause for this effect: the fabled black hole. Here, a black hole shows itself with a parade of light. The connection between a galaxy and the black hole in its heart is not yet well understood. But astronomers recognize that black holes play a part in the formation of galaxies.
As far as we know, every big galaxy has a black hole at its very center. We don't know exactly how this happens. It must have something to do with gas falling in as the galaxy evolves.
And this has been one of the revelations come through a space telescope, is the real deep and fundamental connection between black holes and galaxies done by looking at M87, but also, dozens of other galaxies.
Before Hubble, black holes were merely a concept, an unproven part of astronomical lore. Now we know, black holes are real. In the winter of 1995, a series of commands were sent to Hubble's onboard computer that pointed the telescope toward the constellation of Ursa Majoris, at what looked to be an empty part of the sky. Hubble's powerful gaze locked onto this single region of space for 10 consecutive days, creating a series of exposures that would be known as the Hubble Deep Field.
The Hubble Deep Field was a pretty astonishing idea. Take a telescope out in space and point it at one part of the sky and let it sit. Just take an exposure, and then take another one, and another one, and another one, and then add them all up. And what do you see when you do this? And you see galaxies. Thousands and thousands of galaxies. A crowded, dense field that looks like you're taking a picture of fireflies out in a field at night. And yet this is an empty patch of sky.
Every smudge of light in this Hubble picture is a galaxy containing billions of stars. These galaxies are captured at various stages of evolution. From a time near the birth of the cosmos to the rise of spiral galaxies like our own Milky Way. Scattered here and there in the Hubble Deep Field are the smash-ups of space. Galaxies crashing into and cannibalizing each other.
We estimate that there are hundreds of billions of galaxies in the universe. But it's only until you see that Hubble Deep Field and you understand that you're seeing a tiny little patch of sky. And yet it is filled to the brim with galaxies. And that's telling you that this universe is an astonishing and crowded and wonderful place.
The entire history of growth and change in galaxies is written in this single image of the Hubble Deep Field. What may be Hubble's most profound discovery cannot be seen at all, by any means. Something with so much power, it holds the entire universe together. Astronomers hypothesized that galaxies are surrounded by a halo of unknown forms of matter. This matter acts like a glue that holds the universe together. They called it dark matter. Though we can't see dark matter, one astronomer discovered a way to find it.
We took the Hubble Space Telescope and over 2 years slowly pieced together a mosaic of 600 images, tiled together a large patch of sky in which we could see about 2 million faint galaxies. And this was the Hubble Space Telescope Cosmos survey. It's the largest ever survey taken from space.
The survey revealed that stars and galaxies are born from ordinary matter, trapped by gravity inside clouds of dark matter. This 3D plot of dark matter clouds, charted by Hubble for the first time in history, shows how dark matter forms the very structure of our universe. Soon after the Big Bang, the gravitational scaffolding of dark matter formed the basis for evolutionary change throughout the cosmos.
We, in fact, owe our entire existence to this scaffolding that's set up of dark matter in the early universe.
But what can Hubble tell us about how the universe is changing? Adam Rees was part of a team of astronomers looking for the answer to this basic question. Since the 1920s, astronomers have known that the universe is expanding. They assumed that gravity would one day slow the expansion down and perhaps cause the universe to come to a halt.
I know the universe is slowing down. The question just is how much?
The answer to this question would settle the debate about the age and fate of the universe. Finding the answer became a race.
There were two teams that didn't much like each other. They were trying to measure the rate at which the universe has been expanding at different times in the past and compare it with the rate at which it's expanding now.
The rival team of astronomers was closing on a solution.
There was this sense of competition and urgency to get to the answer. On the other hand, you wanted to be very careful because you knew that, if you got the wrong answer and they got the right answer or vice versa, there would be a way to check.
The way to check comes from Hubble. Hubble finds supernova explosions in remote galaxies, and scientists use the light from the explosion as a yardstick to measure the distance from Earth to the galaxy. But Hubble's findings do not fit the accepted model for the expansion of the universe. The galaxies with supernovae were not just moving away, they were moving at an accelerated rate. Hubble's results convince astronomers that they must think of the universe in an entirely new way. Something is causing the expansion of the universe to accelerate. An unseen force called dark energy.
Dark energy is another manifestation of a familiar force. So gravity is a familiar force, but we've never seen it act this way before. If you had a friend who was sort of Jekyll and Hyde and you had never seen his Mr. Hyde personality, we've seen the Mr. Hyde of gravity, and it's called dark energy.
But the darkest part of this mysterious force is its future. Over time, it will grow in strength. This means that one day, dark energy will become stronger than gravity. Stronger than even the forces which bind atoms together.
Every bound thing becomes unbound, including eventually at the most subatomic level.
Our universe, it seems, is living on borrowed time. The universe will one day end in a cosmic apocalypse that scientists call the Big Rip.
It's what we get for daring to look at something. We're outside the envelope. We didn't expect this at all. It is a tremendous change in how we think about the universe.
Hubble is taking us ever deeper into the universe, to places called deep field and even ultra deep or extreme field.
In the Hubble extreme field, we're able to see more than 12 billion years back in time and find some of the earliest galaxies that formed in the universe.
But astronomers like Jennifer Lotz aren't stopping there. She's looking into frontier fields.
The frontier fields is Hubble's quest to peer deeper into the universe than we ever have before. The concept is to use a trick from Einstein's theory of general relativity. So we're looking at the most massive structures in the universe, clusters of galaxies. And they're so massive that they actually bend space and time, and they act like a natural telescope.
It's called gravitational lensing.
So the combination of gravitational lensing plus Hubble would let astronomers see things that were fainter and farther than we had ever seen before. And we've seen many, many, many very faint galaxies at the edge of the universe.
But what is out there beyond the reach of Hubble?
As amazing as Hubble is, there are certain things it cannot explore. we needed a telescope that could look at other wavelengths of light and reveal what's going on inside dusty, gas-covered regions, which is where stars are born.
Now NASA is building a new telescope, 100 times more powerful than Hubble. The telescope is named after James Webb, the acclaimed head of NASA in the 1960s. It's set to launch in 2018.
Webb can see redder light, which is light that left the galaxies farther back in time than we can see with Hubble. And so we're hoping to see those first stars and first galaxies turn on. That's one of the really big questions for Webb. What will those objects look like?
Webb will be optimized for infrared wavelengths and will cover longer wavelengths of light than Hubble, using a set of unusual mirrors.
Hubble's mirror is about 8 feet across, and James Webb's will be about 21 feet across. But building a single 21-foot across mirror is very difficult to do, so we decided to build it from a series of little hexagonal segments to build up a bigger mirror.
Webb leaves Earth folded up so that it fits on its rocket launch. Once it reaches orbit, 1 million miles away, the telescope expands. Its 70-foot sunshield, the size of a tennis court, stretches out to protect it from unwanted heat and light from the Earth, Sun, and Moon. The James Webb Telescope will take science beyond Hubble's range. But Hubble will always be the first.
Hubble Space Telescope has answered some of our biggest curiosities about the universe and taken things that were in the realm of science fiction and brought them into reality. Scientists today are incredibly excited about using both Hubble and the James Webb Space Telescope simultaneously to study astrophysical objects in a level of detail that we haven't had before.
Hubble and soon Webb, taking the human mind to the beginning and the end of time, beyond our own ability to wonder at the world.